Hello, good evening.
Good evening, sir.
Do you have any doubt from last class to any one of you?
No, sir.
Mehreen, any doubt?
No, sir.
On the basis of last lecture, I had given you assignment and only Mamuna had done. Let me show you. There was a question on Newton's law of cooling, the last topic of radiation. Mamuna did better to solve in the SI unit. So convert this particular time in second first and then try to solve.
Okay, sir.
Although your answer was correct, in this question fourth, let me define you Newton's law of cooling. It states dq by dt with some negative sign. C, that is constant of proportionality, it was 4 epsilon sigma T naught to the power cube A area divided by mass times specific heat times T minus T naught. So from this relation, you will say this rate of cooling will depend upon these factor, epsilon, that is emissivity. Next, area of cross section. Next, mass of object, and then specific heat constant. All these 4 different parameters. You may convert this mass in terms of density into volume. And this area in terms of 4 pi r square. So this r cube and r square may get cancelled out. So you're left with just r. So you'll say dq by dt would be dependent on a radius of that object also. Okay. So in that option, there was specific heat as well as mass. So you'll have to take both mass as well as a specific heat of that liquid. Is it clear?
Yes, sir.
That's it. Okay. So in this thermodynamics, we have started and I had defined you some basic concept about degree of freedom, specific gas ratio, and then real gas and ideal gas. Aisha, any doubt from last class?
No, sir.
Okay. Next is, what do you mean by system and surrounding? Suppose in a vessel, having a piston, gas enclosed, so in this particular part, we mainly have to observe the behavior of gas on different parameters. So system is this whole vessel in which gas is placed and which is under observation is called system. So system is the gas enclosed in a vessel which is under observation is called system. Surrounding is all the influencing factor from outside. We may change the state of gas by any means are called surrounding. All the influencing factor which can affect the state of gas, and system and surrounding combinedly called as universe. Mehreen, any doubt?
No, sir.
Okay, first write it down.
Done, sir.
Now next is types of system. On the basis of exchange of energy and matter between system and surrounding, we may divide the system into three different parts. First is open system, a system which allows exchange of both matter as well as energy to exchange between system and surrounding. That system is called open system, which allows exchange of both matter, energy between system and surrounding. Next is closed system, a system which allows exchange of only energy. Is called closed system. And third, isolated, which restricts any exchange between system and surrounding, which restricts exchange of matter and energy between system and surrounding. Just write it down.
Done, sir.
Mehreen, any doubt?
No, sir.
Okay. Fawaz?
Done, sir.
Okay. Next is Zeroth Law. First law of thermodynamics, but it is defined after first law. So there is no any integer before 1 or a natural number before 1. That is called as 0. This defines the concept of temperature. Suppose you have a vessel like this. There is partition in between. This is any adiabatic wall which restricts any exchange of heat between any two different systems. So it restricts the flow of heat. And this is diathermal wall, which allows exchange of heat. So suppose we have these system A, just one. A, B, and C. So there will be exchange of heat between A and C along this wall, since this is diathermal wall which allows exchange of heat between A and C. Similarly, there will be exchange of heat between B and C, like this. So exchange of heat between any two thermodynamical system will be till they acquire equilibrium or thermal equilibrium. So in first part between A and C, it will be up to temperature of A becomes temperature of C. Similarly, between B and C, it will be till temperature of B becomes equal to temperature of C. So at equilibrium, both these two systems, A and B, is individually in thermal equilibrium with third system. Then if you remove this wall in between A and B, there will be no further exchange of heat between A and B, since A and B will be in thermal equilibrium with one another. Is it clear?
Yes, sir.
Aisha, is it clear?
Sir, can you explain it again?
Okay. We have three independent thermodynamical systems arranged like this. And there is a adiabatic wall in between A and B, and there is the diathermal wall between A and C and B and C. So heat can exchange only through this wall. There will be no exchange of heat through this wall. So heat of exchange between A and C will be till temperature of A becomes temperature of or get equal to temperature of C. Similarly, between B and C, it will be between B and C up to when temperature of B becomes equals to temperature C. So at equilibrium, temperature of A becomes equals to temperature of C, and also temperature of B becomes equals to temperature of C. So both are individually in thermal equilibrium with third system C. So if you remove this wall, there will be no exchange of heat between A and B, since this and this must be at same temperature. So from this entire term, we may define temperature is a physical quantity which defines exchange of heat between any two thermodynamical system. Is it clear?
Yes, sir.
So according to Zeroth Law, it states when two thermodynamical system is individually in thermal equilibrium with third system, then they must be in equilibrium with one another. It means if temperature of A becomes equals to temperature of C and temperature of B becomes equals to temperature of C, then we can say A and B will be also in thermal equilibrium. So from this entire part or zeroth law, we may define about temperature. So temperature is the physical quantity which is responsible for exchange of heat between two thermodynamical system. Mehreen, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Done, sir.
Mehreen, done?
Yes, sir.
Okay. Next is first law of thermodynamics. It is based on conservation of energy. Suppose you have a vessel enclosing a gas So if heat is supplied to this particular system, dq, this heat may be utilized in two different processes. One, to expand this piston from this initial level to this part, or you'll say to increase its work done or to some useful work done by the system to expand this piston from some initial volume to some final volume. And there will be some change in its temperature or change in internal energy du. Similarly, to remove or to extract heat, it must be in combination of decrease in its volume to decrease work done and to decrease its temperature to decrease its internal energy. So from this, you'll say the total amount of heat supplied or ejected must be utilized in two different processes. One, to change the internal energy of that system and to do some useful work. Is it clear?
Yes, sir.
So dq is equals to du plus dw. dq is heat supplied or ejected. Supplied or ejected. du is change in internal energy. And dw is simply work done. So the amount of heat supplied or ejected from the system may be utilized in these two different processes according to conservation of energy, we can say. Mehreen, is it clear?
Yes, sir.
The amount of heat supplied or ejected from the system Okay, just write it down. Abdul Wahid, any doubt? Okay. You all have written?
Yes, sir.
Yes, sir.
Mamuna?
Yes.
Now this particular equation, dq is equals to du plus dw, may be divided into two parts. First is called state function. The physical quantity which depend upon initial and final state of gas, it will be independent of path followed by the gas, is called state function, such as internal energy, entropy. The physical quantity which depends upon initial and final state of gas, independent of path followed, is called state function. So du, change in internal energy, is equals to number of moles times CV times dt. CV is molar specific heat at constant volume. I will define you in later. This particular term is also equals to nR dt divided by gamma minus 1, which may be also equals to n into f divided by 2 times r dt in terms of degree of freedom, or it may be equals to P initial V initial minus P final V final divided by gamma minus 1. So this change in internal energy may be calculated by using these different formula according to the given condition in the question. Mamuna, is it clear?
Yes, sir.
Okay. Now, suppose you have curve like this. Path first, path second, path third. From point A to point B, defined for pressure and volume. So from this graph, you will be asked to relate internal energy change along path 1, path 2, and path 3. Let's say internal energy along path 1 is du1, along second path is this, and along third path is this. So you'll be asked how internal energy along these different paths may be related with one another. Mehreen, which one will be greater, which one will be smaller? According to this graph. Aisha, how these three will be related with one another?
They have the same starting and ending point.
So they must be equal to one another. Good. Just read. According to state function, it mainly depends upon initial and final state of that particular gas. It will be independent of path followed by the gas. So in all these three different paths, initial and final point is same. So the change in internal energy for all these three different paths must be equal to each other, like this. Mamuna, is it clear?
Yes, sir.
Now, similarly, next question will be, suppose you have PV curve. So change in internal energy for closed path. So it is defined by closed integration like this. So this sign defines closed path. So for closed path, initial and final point will be same. So if you subtract, you will get 0. So for any closed path, change in internal energy will be 0. Mehreen, is it clear?
Yes, sir.
Okay, just write it down. Fawaz, any doubt?
No, sir.
Okay.
Done, sir.
Done, sir.
Mehreen, written.
Yes, sir.
Abdul Wahid, okay. Next is, on the basis of sign convention, internal energy, if temperature of system will increase, so du will be positive, and temperature of system decreased, so internal energy will be negative. Next is path function. The physical quantity which depend upon path followed by the gas is called path function. Heat and work done. The physical quantity which depends upon path followed by gas is called path function. So in this part, first, heat. For heat, dq equals to n times c dt. This c is called molar specific heat constant related to that process and that condition, or that given process of gas, isothermal, isochoric, adiabatic, isothermal. Depending upon the process of system, it may have different value. Now, on the basis of this, we may define its sign convention. If heat is supplied to the system, dq will be positive. If heat is ejected out from system, dq will be negative. Aisha, is it clear?
Yes, sir.
Okay, just write it down. You will have written? Fawaz, just 1 minute.
Yes, sir. Done.
Mehreen, done?
Yes, sir.
C is any constant value related to a fixed process. For isobaric, isochoric, isothermal, adiabatic, it simply defines how much heat is required to change the temperature of 1 mole of gas by 1 degree Celsius or 1 Kelvin related to that given process. Fawaz, is it clear?
Okay. Yes, sir.
Now, next part is work done. Work done is equals to force times displacement. We may write force in terms of pressure as pressure into area times displacement. Area into displacement is called volume. So it will be equals to P dV. Integration equals to work done. This is nothing but product of any two different quantity. So in terms of graph, it will be equal to area related to that curve. So area under pressure volume graph will define you amount of work done by the system or on the system. Now, let me define you some term related to this part. In a vessel, there is a gas at some initial condition or at some initial volume, this part. So on doing work by this system, gas, there will be expansion of this piston from this point to reach at this point final. So if you plot the graph of this variation for pressure versus volume, let's say initially condition of gas is at this point for which volume is VI. On expansion, there will be change in pressure or pressure will remain same. It may depend. I'm considering there is small change in pressure so that volume will become VF from VI. So the graph or direction of curve will be from A to B. So according to the concept of work done, it is area under the graph. So this curve will move from A to B and may move like this, and is defined in nothing but a curve along clockwise direction. So the area under this graph will define you amount of work done by this gas on that piston to expand its volume from initial VI to some final VF. Aisha, is it clear?
Yes, sir.
So we can say final volume is greater than initial volume. So the difference of these two terms, V final minus V initial, will be positive. So delta V in this case will be positive. So work done will be positive. And in this case, the gas or the system is doing work on piston to expand it from some initial volume to final volume. So you'll say work is done by the system and related to this, the graph is along clockwise direction. And in this part, volume of gas is expanding or increasing. So you will say expansion of gas. So related to this process, we may define these 5 different terms or for which we have to calculate these different terms. Mehreen, is it clear?
Yes, sir.
Next is, suppose you have a vessel. There is a piston initially at this point. If work is done from any external agency on this piston, which is at some initial volume this point, so there will be decrease in volume to reach at this point V final. So if you plot a graph related to this process, pressure versus volume, it would be like this from point A to point B along this direction. So in this part, initial volume is at this point and final volume is at this point. So if you extend the direction of arrow, you'll get anti-clockwise direction curve like this. So the area under this curve will define you nothing but amount of work done by any external agency on this piston to compress it. Namuna, is it clear?
Yes, sir.
So in this part, V final is smaller as compared to V initial. So if you calculate change in volume, it will be negative. So work done will be negative. In this part, work is done from any external agency on that gas to compress it. So you'll say work is done on the system from any external agency. Next, graph related to this process is in anti-clockwise direction. And there is compression of gas in this process. Any doubt to any one of you related to these two terms? Abdul Wahid? Okay, just write it down.
Done, sir.
Done, sir.
Abdul Wahid, you're done? Mehreen, you have written?
Yes, sir.
From this graph, try to find first part, work done. Second, heat supplied or ejected. Mamuna, just tell me how to calculate area of any curve in physics. Area of circle, area of ellipse. Tell me the formula of calculation of area of circle.
Pi r square.
Okay. And if you have to calculate area of circle in physics, then it will remain same, pi r square. Aisha, any clue?
No, sir.
So Mamuna, which radius you will take? Along x-axis or along y-axis?
X-axis.
Then why there is partially with along y-axis?
Actually, radius all the way, both of them are same, so you can take any of that.
Okay, okay. But in physics, there will be different quantity along different axes. So for any curve, just remember area will be equals to pi r1 into r2. R1 will be along x-axis and R2 will be along y-axis. Is it clear?
Yes, sir.
Is it same for this particular is valid for ellipse as well as circle as well as any curve diagram in whole physics? Try to find R1 along x-axis, R2 along y-axis, and then put in this formula, you will get area required. So in this part, we have to calculate work done. So work done will be area under pressure volume graph. So try to solve. Aisha, any problem while solving?
No, sir.
Okay. Aisha, just send me your answer. All of you just send me your answer for first part, work done. Irene, you got any answer for first part, work done? Aisha? Just see, we have from this point to this point behaving as diameter. Similarly, in this part, from this point to this point, behaving as diameter. So R1 will be diameter divided by 2. So it will be 3V0 minus V0. That is 2V0 divided by 2. So it will be V0. Similarly, R2 for Y coordinate, 3P0 minus P0 divided by 2. So it will be just P0. So work done in this case will be pi R1 into R2. Pi R1 and R2 will be P0 V0. Mamuna, is it clear?
Yes, sir.
Mehreen, any doubt?
No, sir.
Just tell me the sign of this particular work done, whether it will be positive or negative. Aisha?
So positive.
Okay. Mamuna? Positive or negative?
Negative, sir.
Why? Just see, if graph is in anti-clockwise direction, so work done will be negative. If graph is in clockwise direction, work done will be positive. So Aisha, try to check out the direction of graph. Is it clockwise direction or anti-clockwise direction? This graph is going along this way. Is it in clockwise direction or anti-clockwise direction? Mehri?
Anti-clockwise.
Good. So work done will be negative. Next, we have to calculate heat supplied or rejected. So in the above part, I have defined you how to calculate internal energy. So what will be internal energy in this part? Aisha? Just say this. If you have any closed path, So for any closed path, change in internal energy will be 0. Similarly, in this part, since it is a closed term, so change in internal energy will be 0. So use first law, dq equals to du plus dw. This is 0. So the amount of work done must be equivalent to amount of heat supplied or rejected. So dq will be minus of P naught V naught. This minus sign will define you nothing but amount of heat must be ejected from the system. Is it clear?
Yes, sir.
Mehreen, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Abdul Wahid, done? Try to find. Aisha, any problem while solving?
Yes, sir. I'm facing problems doing this.
Let me define this part. Just break this particular curve into two parts according to its direction. One will be P versus V from A to B and then B to C. So it is along this path and this path. Like this. So draw a vertical line to this volume coordinate. So the entire area will define you nothing but work done. For which this point is 2P naught, this point is V naught, and this point is 2V naught. So the area under this graph will be length into breadth. So work done will be 2P naught times 2 minus 1, that is V naught. So in total, it will be 2 times P naught V naught. Now for the next part, for A to C. Pressure versus volume, which is along this. Draw a vertical line to x-axis or along volume coordinate, since it is going along this direction. So the area under this graph will give you work done. So this diagram is nothing but trapezium, for which area will be half sum of parallel sides into perpendicular separation between them. So we have parallel sides P naught from this point to this point, 2P naught from this point to this point, and separation between them 2V naught minus V naught. So work done in this case will be half sum of parallel sides times separation between them 2V naught minus V naught, just V naught. So 2 plus 1, 3, divide by 2, it will be 1.5 P naught V naught. Now for the sign of work done, in first part, since it is along clockwise direction, so work done will be positive. In second part, it is also along clockwise direction, so work done will be positive. So the net work done for this entire term will be 2 P naught V naught plus 3 by 2 times of P naught V naught. So 2 to the 4 plus 3, 7 by 2 P naught V naught, or 3.5 P naught V naught. Is it clear?
Yes, sir.
Yes.
So depending upon the direction, we may break particular curve into different segment, and then we will define work done related to each different path. Mehreen, is it clear?
Yes, sir.
Okay.
None, sir.
Aisha, done?
Yes, sir.
Now, next is thermodynamical process, in which first part is isobaric process, which is also called Charles' law. Iso means same, bar defines you pressure. So the process which is carried out at constant pressure is called isobaric. The process which is carried out at constant pressure is called isobaric. So in this part, P is constant. So change in pressure will be 0. According to ideal gas equation, PV is equals to nRT. So if P is constant, so volume and temperature will be directly proportional to each other. So according equation of state related to this curve will be P volume directly proportional to temperature. So V1 divided by T1 must be equals to V2 divided by T2. Next, according to generalized equation, which was P V to the power x is equals to constant. So if P to be constant, the value of x should be 0. So put the value of x to be 0. So from this part, you will get molar specific heat constant for isobaric process will be termed as Cp. Which will be equals to R divided by gamma minus 1 minus R by x minus 1. So x is 0. So this minus and minus will give you plus. So on solving, you will get gamma R divided by gamma minus 1. Or you replace this gamma in terms of degree of freedom, you will get 1 plus F by 2 times R. Mehreen, is it clear? Aisha, any doubt?
No, sir.
Now, on the basis of this relation, we have to plot graph, 3 graph for expansion related to pressure, volume, temperature. Those are called indicator curve. Indicator diagram. Graph between pressure, volume, and temperature to define the condition of gas is called indicator diagram or indicator curve. So first, between pressure versus volume. Next, pressure versus temperature. And next, volume versus temperature. Since in this part, pressure is constant, so the graph will be straight line parallel to x coordinate. Initial value will be Vi, final value is Vf, and since it is for expansion, so it will be along this direction. Similarly, in second part, if pressure is constant, so temperature will increase from this point to this point. And third part, for volume versus temperature, since these two terms is directly proportional, so graph will be a straight line. So if you have to calculate or relate slope of this particular curve, so just write ideal gas equation. PV is equals to nRT. Move temperature to denominator of volume and pressure to the other side. So you get volume versus temperature, which is nothing but perpendicular by base, and which also define slope of this particular curve. And this particular quantity is related inversely to this pressure. So we can say slope of this particular graph will define you pressure, and it is inversely proportional to pressure. So the greater the slope of volume temperature, it will have lesser amount of pressure. Mamuna, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Mehreen, done?
Yes, sir.
Memuna, done?
Yes, sir.
Now, related to this curve, mainly I have to define for pressure volume curve. First, slope of pressure volume curve. Since this is a straight line which is parallel to x-axis, so its inclination with x-axis will be 0. So tan 0 will be 0. So you'll say dp by dv will be equals to 0 related to isobaric curve. Next, on the basis of this curve, we may define the value of bulk modulus beta, which is equals to dp by dv multiplied by volume. dp by dv is 0, so this whole term will be 0. So you'll say bulk modulus for a particular system is 0. It means there will be no elastic behavior of that particular system. So isobaric process, or for isobaric process, there will be no elasticity. Next, we may define amount of work done. So work done is nothing but area under pressure volume graph. So pressure is constant. So it will be V final minus initial. PV is equals to nRT. So we may write nRT final minus T initial. Now we have work done. And since it is isobaric process, so we may calculate heat dq equals to n times c dt. And since this particular process is the isobaric process, so the c will be nothing but cp, which is equals to n gamma r dt divided by gamma minus 1, or it should be equals to gamma divided by gamma minus 1. In terms of pressure volume, it will be P final V final minus P initial V initial. So there will be a relation between work done, heat, and internal energy for this isobaric process. dq is equals to gamma times du, which is equals to gamma times dw divided by gamma minus 1. So just remember this particular relation. If you have to calculate heat, internal energy, or work done, try to find work done related to that particular curve. Use this relation to find amount of heat supplied or ejected, or amount of change in internal energy of that particular process. Aisha, is it clear?
Yes, sir.
Okay, just write it down. Aisha, done?
Yes, sir.
Let me give you a question related to this part. For helium, graph for pressure versus volume is find first work done, second heat supplied. Use 1 atm equals to 10 to the power 5 Pascal and 1 centimeter cube equals to 10 to the power minus 6 meter cube. First, try to find work done. First, try to find work done and send me your answer. Then I will define you how to calculate heat. Good, Mamuna. Mehreen, you got the answer for first part, work done? Aisha?
No, sir.
Okay. Just see this. This first part. How to calculate work done in terms of isobaric process. So work done is pressure times V final minus V initial. Okay. Or just area under the graph, we can say. Aisha, is it clear?
Yes, sir.
So in this part, we have pressure of 2 atm and change in volume from 2 centimeter cube to 4 centimeter cube. So work done will be equals to pressure V final minus V initial. Pressure is 2 atm. So 2 into 10 to the power 5. Change in volume is 4 minus 2. And since it is in centimeter cube, so multiplied by 10 to the power minus 6. Is it clear?
Yes, sir.
So 4 minus 2 will be 2, 2 into 2, 4, 10 to the power 5 and 10 to the power minus 6. So it will be 10 to the power minus 1, or it will be just 0.4 joule. Mehreen, is it clear?
Yes, sir.
Now just see, in this part, we have given helium gas. Tell me the nature of this particular gas. Is it monoatomic, diatomic, triatomic, polyatomic? Mamuna? Helium is monoatomic, diatomic, triatomic? Which type of gas?
Monoatomic.
Good. So helium is monoatomic. And for monoatomic, degree of freedom, F will be 3. So from which we can calculate gamma, which is equals to 1 plus 2 by F. Put the value of F to be 3. So you'll get 5 divided by 3. Aisha, is it clear?
Yes, sir.
Now use this relation. We have work done. We have gamma. Just equate this. You'll get amount of heat supplied to the system as well as internal energy. Aisha, you got any answer?
I'm doing it, sir.
Okay. Good, Memona. Let me solve dq equals to gamma divided by gamma minus 1 times work done. Gamma is 5 divided by 3 whole divided by 5 minus 1 times work done 0.4. So in numerator, we have 5 by 3. On solving this fraction, 5 minus 3, it will be 2 divided by 3 multiplied by 0.4. So this 3 and this 3 will cancel out. So you're left with 5 by 2 into 0.4. So 5 into 4 will be 2 divided by 2. It will be just 1 joule. Aisha, you got this?
Yes, sir.
Good. Mehreen, any doubt?
No, sir.
Okay, just write it down. Mehreen, done?
Yes, sir.
Okay, so do you have any doubt related to this entire part from today's class to any one of you?
No,
Aisha? Okay, so let's stop here for today. In next class, I will define you the next process, that is isochoric, isothermal, adiabatic. Okay?
Okay, sir.
Okay then.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.